Welcome to the playlist for Math 151 at Jackson College. This is Calculus 1. And we're going to be taking a look at our three major topics of calculus in this class: limits, derivatives, and integrals. We'll begin in Unit 1 by talking about the idea of limits. Limits are interesting in and of their own right, but they're also interesting because they're going to feed all of the other calculus topics that we'll look at as we go through this course. So Unit 1, we'll look at limits. We'll start by getting sort of an idea of what they mean. We'll look at them visually. Then we'll move into how we calculate them. And then finally we'll finish up with some situations where limits actually inform our decisions in real life. So let's begin. As I said, we'll start by talking about limits from a visual standpoint. And in math, visually usually means graphically. So this is Unit 1, Topic A, finding limits graphically. I'm going to look at this kind of crazy graph, and I'm going to assume that this is the graph of some function, y equals f of x. Clearly we aren't given a formula. We're simply given the graph. The formula would have to be piecewise, right? It's kind of a crazy looking graph. I'm also going to say that in general, I'm going to ask that you always assume when we see a sort of a trend happening, that you assume that that trend continues. So for example, on the left-hand side here, we'll just assume that that continues to go down and to the left forever. We'll look at more like that as we talk about limits. All right, I'm going to begin by concentrating on the x value -4. And the first question that we're asked is, what is f of -4? Well, that's not terribly difficult to answer. When I look at -4, the y value doesn't exist. That little hole in the graph means there is no y value. So I'm going to say f of -4 does not exist. And since does not exist is something we're going to be writing a lot, I'm going to abbreviate that as DNE. Now, we get into the concept of the limit. When I talk about the limit, I'm not talking about what happens right at -4. Instead, I'm talking about what happens close to -4. So here's the notation that tells us that. Instead of asking at what is f of -4, or in other words, what's the y value when x is -4, we say what is the limit, LIM for limit, as x approaches -4 for this function f of x. So when I think about this on my graph, here's my -4 again. And rather than looking at x values right at -4, I'm going to let the x values approach or get close to -4. Maybe x values like this that get closer and closer to -4. Let's look at what happens to the y values. Well, let's see. If I just kind of mark on the graph where the y value would be for each of those x values that I just selected, I can see that my y values are getting closer and closer to 3, which implies that the limit is equal to 3. In fact, I'm going to write that right now, and we'll talk more about it. A couple things. First of all, notice that I'm never going to actually hit the value of 3. Right at -4, that y value really doesn't exist. Y is never actually equal to 3. It's just when x gets close to -4, this is saying y gets close to 3. As we're going to see in some of the other problems, it's not actually sufficient for me to just say, hey, let's sort of come at this -4 from the left side here. I have to be able to come at this from both directions in order to truly make this statement. So I also have to be able to approach -4 from the right. I can do the same thing, notice. I can pick some x values. They get progressively closer to -4. And I can see that once again, for these points, the y values get close to 3. Oftentimes, to sort of show this visually, we'll show it using arrows. We'll say that as x gets close to -4 from the left, the graph approaches that missing point. And I can do that same thing, coming towards -4 from the right. Once again, the graph approaches that missing point, or approaches the y value of 3. All right, let's go ahead and take a look at some other points on this graph. The next question asks about what's going on when x is -2. So here's -2 on my graph. And from our past math experience, we can kind of see this looks like it's probably a vertical asymptote. This graph appears to be continuing to go down on the left and also down on the right. It doesn't actually hit the line, the vertical line at -2. It just seems to be getting close to it from both sides. So it's probably a vertical asymptote. That means that the actual y value, once again, does not exist. Notice we've now seen 2 different cases where that can happen. This little hole in the graph, almost like a little missing point, can mean the y value doesn't exist. Or on a vertical asymptote, the y value doesn't exist. What happens this time as x approaches -2? Well, as we approach -2 from the left, the y values continue to get very large in the negative direction. And the same thing happens coming in from the right. As I approach -2 from the right, the y values get very large in the negative direction. So I'm going to call that limit -infinity. All right, the next point of interest is when x is -1. What is f of -1? Well, notice this time here at -1, this would be -1 right here. Here at -1, there is this little hole in the graph, but in fact, there's also an actual point above it. So f of -1 does exist. This point with its y value of 5 represents f of -1. But what's the limit as x approaches -1? Well, if I think about the graph, as x gets close to -1, the graph doesn't get close to that point there with y of 5. The graph actually gets close to that little hole. In fact, if I were to be casually sitting here with my pen accidentally covering up that point, you probably would think that the point was even there. Right? So that point has a y value of 1. And I'm going to say the limit as x approaches -1 is 1. All right, what happens at 0? And because this is going to get too far away for us, I've made myself an extra little graph here so we can see it as I move my paper up. At 0. Well, at 0, it looks like we have another vertical asymptote. So I'm going to once again say that the y value does not exist. But what about the limit as x approaches 0? As we approach 0 from the left, the y values on the graph seem to be going up. They get very large in the positive direction. And as I approach 0 from the right side, all the y values in the graph here get very large in the negative direction. So in this case, what happens to my graph, what happens to my y value, depends on which direction I'm approaching the value of x equals 0 from. In order to state that, we need the concept of one-sided limits. What I'll say here is that the limit as x approaches 0 from the left for the function f of x, so coming from the left side, this function was getting very large in the positive direction. So that limit would be positive infinity. However, I'll also say that the limit as x approaches 0 from the right side of f of x, so now I'm looking at starting on the right side and coming back towards 0. Now my graph is going down towards negative infinity. When you have one-sided limits, limits from the left and from the right, that are not the same, you say that the two-sided limit, the limit as x approaches 0 without stating left or right, for the function f of x does not exist. By the way, I use the notation somewhat casually, but let's just go back and take one more look at it. Again, the little minus sign here indicates that I'm coming towards 0 from the left side. So here's 0, I'm coming toward it from the left, and the graph was going up to positive infinity. This little plus sign indicates that I'm approaching 0 from the right side. So I start to the right of 0 and come back towards 0 from the right side, in which case the graph went down toward negative infinity. So these little negative and positive signs don't necessarily mean negative and positive numbers. They indicate which direction we're approaching the x value from. All right, let's take a look at what's going on at 2. When x is 2, right here, it looks like I do have a y value. There's a solid dot right there. So that's the point on the graph that corresponds to x equals 2, and it has a y value of 1. So f of 2 is equal to 1. Now what about the limit as x approaches 2? Well, as I'm approaching 2 from the left side, I can see that on the graph, it looks like I'm headed toward that solid dot, or toward the y value of 1. So I can say the limit as x approaches 2 from the left side for f of x is equal to 1. Now what about if I approach 2 from the right side? Start on the right side of 2, get close to 2. The points on the graph that correspond to that would be the ones down here. And notice that although we never hit it, it looks like the y values were getting very, very close to negative 1. So I'll need to say that the limit as x approaches 2 from the right side for f of x is negative 1. Again, the left side and the right side, the one-sided limits do not match. And therefore I have to say that the two-sided limit, just the limit as x approaches 2 of f of x, does not exist. Typically, we don't bother writing out the one-sided limits unless they're going to disagree. And that's just sort of a way of showing or proving that the two-sided limit doesn't exist. All right, a couple more. Let's look at 4. X equals 4. That would be right here. And as I look at this one, I can see once again we're looking at a vertical asymptote. There is no y value there. It's very likely that this was intended to keep on going up forever. Again, when you see a trend like that, feel free to make that assumption. And so I'm going to have to say f of 4 does not exist. Now what about the limit as x approaches 4? If I let the x's approach 4 from the left, the graph is getting very large, towards positive infinity. If I let x approach 4 from the right side, the graph is also getting very large, toward positive infinity. And so this time, I don't think I have to write down the one-sided limits because I think they're the same. From both sides, this graph approaches positive infinity. So that's my limit. All right, we've got one more down here. We want to look at the limit as x approaches -5. So -5 would be right here. And f of -5, notice, does exist. This point in the graph is not even marked because it's so perfectly well behaved. Nothing weird happens here, right? So at -5, the y value is 0. And we'll say f of -5 is equal to 0. Now what about the limit as x approaches -5? Well, as I approach -5 from the left side, the y values in the graph approach that point, 0. And as I approach -5 from the right side, the y values in the graph also approach 0. So the limit here will be 0. I'm jumping the gun just a little bit, but a situation like this, in which the function value and the limit are exactly the same, is actually a special situation called a continuous point. We'll talk a lot more about the idea of what it means to be a continuous point toward the end of this chapter, but I'm going to point it out to you right now as sort of a preview of coming attractions. Points like this, where nothing weird happens, everything just sort of seems normal, are usually continuous. Their function value and their limit agree. All right, we'll take a break and we'll come back and finish part A in the next video.